Good afternoon, students. Can you see my writing pad?
Good afternoon, yes, sir.
Okay. I want to talk about what a fractional capacitor is. And then I want to talk about how we could approximate it in the real world. And then I want to talk about the handout I sent you all last night. So the impedance of a regular capacitor is what? What's the impedance of a regular capacitor? What's the impedance of a regular capacitor?
1 over j omega c.
Yes, 1 over C. Okay. So what's the magnitude of the impedance? What's the magnitude of the impedance?
One over j omega c.
Really? The magnitude of the impedance is the same thing as the impedance? I don't know why y'all can't get this right. What's the magnitude of the impedance? What's the magnitude of a ratio? The magnitude of the top over the magnitude of the bottom. What's the magnitude of 1?
1.
What's the magnitude of j omega c?
Omega c.
Omega c. Omega c. What's the angle of the impedance?
Is the angle of the top minus the angle of the bottom?
All right. Angle of 1 minus angle of J omega C. What's the angle of 1?
0.
0 degrees. What's the angle of J omega C?
It's that tan inverse of
What's the angle of J omega C?
would it be inverse tan omega C of omega C?
No. What's the rule?
Sorry, but I misread 2006.
Excuse me? Miss Adley, you were saying something?
No, I say misread my hand.
Well, the rule is tan inverse of imaginary over real.
What's the imaginary? What's the imaginary?
J omega.
No, absolutely not. I don't know why y'all won't learn this. We did this in 120. We did this in 235. We did this in 320. And y'all still don't know it. What's the imaginary part of J omega C?
Hey,
Excuse me?
J omega.
Somebody just said that, and I told them no. The imaginary part is not an imaginary number. I keep telling you all this. The imaginary part is not an imaginary number. The imaginary part is a real number. The imaginary part is the coefficient of J.
Yeah, obviously.
Not honestly, because y'all still ain't gave it to me right yet.
J on the y-axis, right?
What's the imaginary part?
In this one, what you have up here?
Yes.
1?
I'm dealing with this. What's the imaginary part?
I know there. They have all of them. The whole dimension. No, that's probably not.
1. J.
Absolutely not.
J.
Absolutely not.
C.
The imaginary part is the coefficient of J. What's the coefficient of J?
1.
The coefficient of J is not 1.
Omega.
My God. You don't need to go back to elementary school.
But all the guy, right? If this say if it's no number in front of the J, wouldn't the coefficient be 1?
It is not the number in front that's the coefficient. It's the number multiplying that's the coefficient.
Omega C.
Yes, omega C is the imaginary part. Omega C is the imaginary part. Therefore, what is the phase?
Would it be 180?
I don't know why we're guessing. Why you guess 180? What's the phase of J5? I mean, what's the phase of J? What's the phase of J5?
Would phase of J5, would that be 0 degrees?
Wow. I don't know when y'all intend to learn this. There's 1. There's J1. There's -1. There's negative J1. Where's J5? This is J5. There's J5. How long is J5? J5 is 5 long. What's the angle of J5? It's 90 degrees. Why don't you all know this? The phase of J5 is 90 degrees. The phase of J omega C is 90 degrees. Because omega C is a positive number. Negative degrees. So the angle of the impedance of a capacitor is negative 90 degrees. When are y'all going to learn this? This must be now the 100th time I'm showing you all this. This angle here is 0 degrees. So 1 is the same thing as 1 0 degrees. This angle here is 180 degrees because angles are measured relative to the positive x-axis. So -1 is 180 degrees. And this angle down here is 270 degrees or -90 degrees. So negative J1 is 1 270 or it's 1 -90. You need to learn this. That's a regular capacitor. This is a regular capacitor. So if we were to plot 1 over omega C versus omega, okay, and we do a Bode plot, we'd be plotting the impedance in dB, you're plotting the impedance in dB, okay? And versus log scale, it'll look like this. The slope of this would be negative 20 dB per decade. Okay? And this would be 20 log 1 over omega c. So that'd be the impedance. That would be the impedance in dB. And this would be log omega. And then the phase would be negative 90 degrees. No matter the frequency, the phase of a capacitor is negative 90 degrees. Now, we can define a fractional capacitor whose impedance I thought Mr. Kerr was trying to get in. Impedance is given by 1 over S to the power of alpha C. And clearly when alpha is 1, we're dealing with it with a regular capacitor. This is a fractional capacitor. A fractional capacitor. All right. I'm going to change slides. And right now, let's discuss alpha equals 0.5. So the fractional capacitor we're dealing with let's call it CF. CF is 1 over the square root of S times C. So it's 1 over root J omega times C. So that's 1 over root J root omega times C. Let's call it CF. Or C.5. Impedance. C.5. That's a fractional capacitor. This capacitor does not exist in the real world. This capacitor we have to approximate. We can't build this capacitor exactly. We can approximate it. Nonetheless, a lot of theoretical work is being done with such a capacitor. What's the square root of J equal to? I bet nobody can tell me.
-1?
No. J is -1. J is the square root of -1. So square root of J is the square root of the square root of -1, which is -1 to the power of 0.25.
Oh, okay.
J is also equal to E to J pi over 2. You should know this. You should know this because you should know Euler's identity. You should know that E to Jx equals cosine x plus J sine x. You should know this. So then E to J pi over 2 equals cosine pi over 2 plus J sine pi over 2. What's cosine pi over 2? What's cosine pi over 2?
One.
Please put pi over 2 cosine into your calculator and tell me what the answer is. Pi over 2 is in radians. Make sure you calculate in radians.
I put in radians now. It's a 0.
What's a 0? What's sine pi over 2?
One.
1. So that proves my point. Okay. See right here? J is E to J pi over 2. So this up here is 1 over square root of J. And the square root of J is the square root of E to J pi over 2. Square root omega times C. Okay. And E to J pi over 2 square root is the same thing as E to J pi over 2 to the power of a half. Square root omega C, which is 1 over E to J pi over 4. Square root omega C. So then the magnitude of this fractional capacitor, is the magnitude which is 1 over the magnitude of E to J pi over 4 times the magnitude of omega C, which is the magnitude of this is 1. So this is 1 over root omega square root omega C. That's the magnitude. This is the magnitude. This is the magnitude of this fractional capacitor. We plot the magnitude of this. We plot the magnitude of that. And it looks like this. Where the slope here is negative 10 dB per decade. Negative 10 dB per decade. And what's the angle? What's the angle of this? What's the angle of this? The angle of that is the angle of the top. So the angle of this fractional capacitor is the angle of the top. Angle of 1 minus the angle of the bottom. Okay. and the angle of this is just pi over 4, and the angle of this is 0. So it's negative pi over 4, and pi over 4 is 45 degrees. 45 degrees. So the phase of this capacitor is negative 45 degrees, no matter the frequency. So this is how this fractional capacitor differs differs from a regular capacitor. When you plot the magnitude of the impedance, a regular capacitor is negative 20 dB per decade. This fractional capacitor would be negative 10 dB per decade. Okay. Any questions so far? All right.
Can I get the snip of the second page, please? Thank you.
All right. Now, again, let me emphasize. Is a theoretical capacitor. Okay. This is approximately equal to, okay, we can approximate this, okay? Square root of S is approximately 3S plus 1 over S plus 3. Don't worry about where I got this from. It's also approximately okay. This is a first order approximation. And this is a second order approximation. Okay. So this here then is approximately 5S squared plus 10S plus 1 over S squared plus 10S plus 5 times C. And these are valid. And of course, we can have a third order approximation and fourth order approximation. Okay. And these are valid around S equals J1. In other words, omega equals 1 rad per second. That's when they're valid. Let me show you that. Show you that in Octave. What does that line say? What am I telling Octave to do? I am telling Octave to create omega values, logarithmic space between 0.1 and 10. And then I'm gonna put a semicolon because I don't want to print it out. Okay, so S equals J times omega. So mag 1 is the magnitude of the square root of S. Okay, that's what I want. Okay, and I want that in dB. dB1 equals 20 times log 10 of mag 1.
Dr. Goddard, what does ABS means again?
What is what?
ABS mean again?
Absolute value.
Oh, yeah, that's a.
Okay. And then mag 2, then H, then Z2 or prox, we call it Z2. Impedance 2 is what? I said it was 5 times S plus, I'm gonna need dot times. Plus 10 times S plus 1. Dot divide S dot times S plus 10 times S plus 5. So this is approximation. This is the second one approximation. Okay. And so I want the magnitude of that. Magnitude 2 equals ADS of Z2. And then I want dB of that. dB2 equals 20 times log 10 mag 2. Okay. And now I want to semi-log x omega comma dB1 comma omega comma dB2. Okay, and now let me save that. And let me see if that works. So I remove the M. I remove the edit. I call the file. And there it is. Okay. Okay. And the blue is the square root of S. Okay. The blue is the square root of S. And the red is the approximation. The red is approximation, which you see is pretty good around omega equals 1. And let me just broaden this so you can see what happens. So let's go to -2. The 2. So from 0.01 to 100. File, save. And there it is. So the square root of S, the magnitude of the square root of S, I should say, is the blue. That's the theoretical. That's what we want. Okay. That's what we want. That's not the capacitor. That's just the square root of S. The red is a second order approximation to that. Okay. That's the 5s squared plus 10s plus 1 divided by s squared plus 10s plus 5. That's the second order approximation to that. So that's for the magnitude. Okay. That's for the magnitude. Now let's do the phase. Okay. So let me just plot the phase now. Phase 1, comma, omega, comma, phase 2. Okay, and we need to define what phase 1 and phase 2 are. Okay, so phase 1 is the angle of the square root of S, which I said was 45 degrees. Angle of square root of S. I need another bracket there. Times 180 divided by pi, because I wanted, okay. And phase 2 is the angle of Z2. Okay. Times 180 divided by pi. Let me save that. And let me see if I didn't make any errors. And I did. I got too many brackets. And there it is. See, my ideal is 45 degrees. That's a blue line, 45 degrees, no matter the frequency. But my second order approximation gives me 45 plus or minus from about this value to about this value in frequency. So it gives me 45 degrees plus or minus a small number over a limited range around 1 rad per second. Okay. So I just showed you what I just showed you is this approximation. This is a good approximation for the square root of S for frequencies around 1 rad per second. Okay. All right, now let's see how we use that to actually build a capacitor, a fractional capacitor. Give me a second, please. So we want to implement this fractional capacitor. We're going to make C equals 1 farad. So we want some impedance to be 1 over root S. And I just showed you that is approximately 1 over 5S squared plus 10S plus 1 over S squared plus 10S plus 5, which is S squared plus 10S plus 5 over 5S squared plus 10S plus 1. So this is the impedance we want to implement. That's the impedance we want to implement. Get me to the roots of that quadratic, please. Send me answers in chat. Mr. Roll, please give me numbers. Mr. Johnson, that don't look right at all.
Yes, sir. I have a question. Is that 2S or is that 25? Because I took it as 2S.
It is 2S.
Okay.
It's a quadratic in S. So why is there any doubt?
I took A as 1. It's supposed to be 5. That could be my only mistake I going off on.
Excuse me?
I took A as 1 instead of 5. That could be the only mistake I didn't get going off then. I guess I had to look good.
Okay. I got two answers, but neither of those look right.
I got the right answer. Just give me 1 minute.
Mr. Johnson, your last answer is completely wrong. Absolutely completely wrong.
All right.
I asked for the roots of that quadratic. And only two people get to answer. S equals -2 divided by 2 plus or minus 4 minus 4 times 0.2 divided by 2. -1 plus or minus the square root of 3.2 divided by 2 minus 1 plus or minus 0.8944 equals minus 1.8944 or minus 0.1056. Now, nobody got this. Nobody can find the roots of a quadratic. In a 400 level class,
Dr. Cartwright, you forgot the A in the square root. B squared minus 4AC. I only see
what is A?
A would have been 5.
No. Look at the quadratic I'm talking about. The quadratic does not include the 5.
That would have been 1.
Keep that in mind. Okay. So we have, ignore the 5 right now. So S squared plus 10S plus 5 divided by S squared plus 2S plus 0.2. So it's 1 S squared plus 2S plus 0.2. And that's 8S plus 4.8. Okay. So this here is 1/5, okay, times 1 plus 2S plus 0.2, okay, over S squared plus 2S plus 0.2. Okay. Okay, I'm going to another page. So then the square root of S is approximately 1/5 plus 2/5 0.4, okay, plus 0.2 divided by 5, 0.04 over S plus 0.1056 times S plus 1.8944. Now, get me the partial fraction expansion of that. I want the partial fraction expansion of that. Send me your answers by email. Come on, folks, I'm running out of time here. All right, pay attention, please. This would be plus A over S plus 0.1056 plus B over S plus 1.8944. And what's the A equal to?
Negative 0.1056.
I doubt that. I doubt that very much.
You mean after you calculate it, sorry. Well, I got
A
negative
A is
0.00125.
4S. A is negative?
That's what I got, but I might have calculated wrong.
A equals 0.4S plus 0.04 over S plus 0.18944. Evaluated S equals negative 0.0156. So that's 0.4 negative 0.1056 plus 0.04 or negative 0.1056 plus 0.18944.
I get 0.0013. You double check.
Okay, let me see what this is. Plus 0.4 times 0.1056 negative plus 0.04 negative 0.000224 divided by 0.18944 minus 0.1056 over 0.08384. And that's negative. And that's a problem. That's a problem. Where did I go wrong? Give me a second here. Oh, okay. I see where I went wrong. This is supposed to be 8S. 8S plus 4.8. Okay. Because it's, it's the answer here that goes up here. So that would make 805. That would make this 1.6. 1.6S. And it would make 4.8 divided by 5. Make this 0.96. So this is 1.6, 0.96, 1.6, 0.96. Okay. Uh-oh. Okay. So that's negative 1.6 times 0.1056 plus 0.96. That's 0.799 divided by 0.18944 minus 0.1056. 0.08384 equals 9.435. 9.435. So this is now 9.435. Okay.
Dr. Godray,
Yes?
for B, I know this answer right, but I was getting 1.158.
What did I do wrong then?
I know you solved for B, yeah?
I ain't solved for B yet.
Oh, yeah.
So you saying that's B?
No, I do solve, but we can work it out. I get 1.158.
Let's do B. Let's do B now. So B is 1.6s plus 0.96 divided by s plus 0.10, s equals negative 1.8944. So that is 1.6 times 1.8944 minus plus 0.96. That's negative 2.0710 divided by 1.8944 negative plus 0.1056 negative 1.7888, and that is 2.0710 divided by 1.7888. 1.158. Is that what you got?
Yeah, that's what I get.
Okay, so this is 1.158. Okay. Here's the deal. Let's not lose sight of what we're trying to do. What is this? Tell me what that is. Wow. See, we already lost sight of what we're trying to do.
I know that's 1 over square root of S, and that's, are you using that to kind of this, because it's close to the fractional capacitor?
No, that is the fractional capacitor. This is the impedance of the fractional capacitor, where C is 1 farad, we said.
Yes, sir.
Okay, let's go back. See it here? Here's the fractional capacitor. 1 over square root of S times C at the bottom. And we said C is 1 farad. So this is impedance. This is impedance. Impedance is this plus this plus this. Impedance, that impedance is Z1, that impedance plus Z2 plus Z3. So that impedance, using the second order approximation, is the sum of three impedances. What's the first impedance? What's the first impedance? If I give you impedance equals 1/5 ohms, what is that? What component is that?
Oh, you mean the resistor?
That's a resistor, yes. So our fractional impedance is approximately a resistor. Of what value? 0.2 ohms. In series with, I know they're in series because we're adding them. In series with C2, I will tell you what that is. That's these two things in parallel. In series with C3. So that capacitor then, this fractional capacitor, this ideal component is nothing more than 0.2 ohm resistor in series with this parallel combination. Let's call that R1 and this C1. Let's call that R2 and C2. Now, how can we find the values of R1 and C1, R2, and C2? Okay. Take a shot of this, please, because take a snip of this. Six. In general, then, what's the impedance of these two things in parallel? Any resistor here. Any resistor and any capacitor. What's that total impedance? What's that impedance? What's the impedance of that resistor and that capacitor in parallel?
Is that 1/SC times R all over 1/SC plus R?
Yes. It's R in parallel 1/SC, which is R/SC plus R plus 1/SC. Multiplied top and bottom by SC, R/SRC plus 1 equals R/RC over S plus 1/RC equals 1/C, S plus 1/RC. So that parallel combination is this. Okay. Well, what is Z2? Z2 is 9.435 over S plus 0.1056. This is Z2. So that must mean 1/C is 9.435, or C equals reciprocal of that.
So we can use that to solve for R then.
Absolutely. You're ahead of me, though. Stay with me. .1060 farads. And then this must equal this. Okay? So 1/RC. 1/RC must be 0.1058. Okay? or 1 over C times 0.1058 equals R.
956.
5, 6, thank you. Thank you for paying attention. So
You can change it in
that's,
the denominator too.
excuse me? Oh,
I'm
okay,
saying-
yeah. I see what you mean. So that is 0.1060. Okay. Okay, that's C times 0.1056 reciprocal. So that's 89.34 ohms. But somehow that don't seem right.
Can we check A value one more time, please?
Excuse me?
Say, can we check that A value one more time? That's the 9.435.
What do you think is wrong with it?
I mean, I got the same thing for B, but my A value is different from yours. I wonder.
What you got for A?
All right, let me check. I got 0.4422. 0.4422. I might have calculated wrong. Just wanted to make sure.
Anybody else? Okay, let's see. So 1.6 times 0.1056 minus plus 0.96, 0.7910, that's good. 0.18944 minus 0.1056, 0.08384 reciprocal times 0.7910.
What Tori say you got for A?
9.435. I don't see where I went wrong. All right. Give me a second here.
I know I for A getting 1.372. Double check that again.
Will you all see what I'm doing wrong?
I wonder if you left out the negative, well, negative 0.1056.
Where?
No, the write-up's right. It look right.
Hmm?
The write-up look right.
So am I computing it wrong?
Let me see, 0.96. Now, oh, I had the wrong value. I had 1.6, but now I getting 0.813.
What that is in the denominator, is that 0.18944? I thought it was 1.
Yeah, it's supposed to be 1.8944.
Yeah,
4.
1.8944, not
And the
0.
denominator, the way you have A equal, it's supposed to be 1.6 or 0.6? Is 1.6.
No, it's not.
I'm talking about where you have A. A equal 1.6S.
Yeah, what's wrong with that?
In your denominator, you see you have S plus 0.8944. Isn't it supposed to be S plus 1.8944?
Yeah, 1.8944. You have 0.1.
894.
Yeah,
in your denominator.
your denominator. I was trying to figure out how to get the 0.18944. Because if we look at Z3 and the denominator is
I think he screen freeze or something.
Oh, okay.
What was the resistor value, guys? What would we to calculate just now?
I think it right.
No, it might not be right.
I recalculate for R and I get 893.
Yeah, that's where you going wrong, Dory, because I getting A equal 1.372.
Okay, yeah. Yeah,
That's
I think
what
that's
you
where
get,
we're going wrong.
I get 1.372. That's A.
Okay.
Okay, I wrote down.
I guess we could wait a couple of minutes more. Not that long.
Okay, I'm back.
Yes, sir.
Okay.
But you saw what we were saying, Dr. God, right?
Hold on a sec. Here we go. So I got 0.4422. You'll agree with that?
Are you getting 1.372?
Well, what am I doing wrong?
No, I get the 0.44 just now. I had to do it again. Try putting it again, Sam.
Dr. Carter, what did you get for your R value when you first calculated? Could I see that?
My R value, that's wrong. My R value is wrong because the 9.434, the 9.435 is wrong. So this is now 0.4422. Okay. So 1 over C then, 1 over C is 0.4422. So C is 0.4422.
I
Reciprocal
think you going on.
2.2261. Okay. All right. Here's the deal. Here's the deal. Yeah, I don't want to rush through this. My time is gone. So here's what I want you to do. Here's what I want you to do. I want you to confirm. I want you to find the partial fraction expansion of this. That's what I want you to do. All right. And then from that partial fraction, we will discover that impedance, that approximate impedance, is the sum of 3 impedances. And we will discover this is a resistor, this is resistor and capacitor in parallel, this is resistor and capacitor parallel. And we'll take this up on Wednesday. Okay.
Look like Wednesday is our last class.
No.
And
We got
Friday,
next.
Monday.
We got next Wednesday. We got a week from Wednesday.
Well, I thought you're studying for the exam on that Wednesday.
Let me tell you what.
Question.
Excuse me. Excuse me.
Ask questions.
Ask questions.
Yeah.
Who you gonna ask questions of?
The last 2 times, any misunderstandings, you allowed us to ask, like, questions, I guess.
Yo, man. It's not my job to study. It is your job to study. Anyway, this is what we'll do on Wednesday. And depending how far we get on Wednesday, I will let you know whether or not I'll give you next Wednesday off as well. But it depends how far we get on this Wednesday. So if you want next Wednesday off, come prepared. Do what I asked you to do. So the goal is to get this value. That will be 0.2. Any question about this? The goal is to get R1, C1, R2, and C2. That's the goal. Any questions about what I want you to do?
Can I have a word with you after class?
Yeah.
And can I just see page 6 before we go, please?
Yeah. These values are wrong.
Right.